Welcome to September's BTS evening presentation. I hope you all had a good summer, and it's great to see so many people here. Really appreciate that. So I'm sure we're going to have a good evening. We're on our talk on Coire Glas project. So tonight is the first time we've had a combined meeting between the BTS and the BTS young members. It's something I'm very keen on, to try and join up the two organizations wherever possible. So part of that was we have some speakers tonight who are also young members, and Arabelle, who is the current chair of the Young Members BTS, is joining me tonight to help out. So yeah, hopefully we'll make this an annual event, that we have a combined meeting, and we'll see where it goes from there. So moving on, our speakers tonight then. So it's on the Coire Glas project. First, we have Joe Coxson. He's a tunnel agent at STRABAG. Joe is a chartered engineer. Between studying mining engineering in Cornwall and joining the Coire Glas project in the Highlands of Scotland, Joe has worked underground across the full length of the UK. His 10 years in the industry have been wide-ranging, including SCL tunnelling in Whitechapel and Liverpool Street stations for Crossrail, and TBM experience on the cooling water tunnels for Hinkley Point C and the MTS drive for the Woodsmith mine. For those who know Joe will understand Coire Glas was an obvious dream project, as not only is he enthusiastic about drill and blast works, but when he's not underneath the mountains, he's often found clinging to the side of them by his fingertips or ice axes. Our second speaker is Tom Robinson, engineering and technical manager for STRABAG. Tom is a chartered geologist with 14 years of tunnelling experience. Tom is an experienced on-site manager of tunnelling and geotechnical works, including SCL and TBM tunnel production in a broad range of ground conditions, from soft clay and running sands to hard rock, and managing ground investigations in hard rock. Tom led the procurement planning and on-site management of the Coire Glas Exploratory Works GI phase for STRABAG UK, culminating in submission for the final factual GI report in May 2025. Tom also has experience in quantity and cost estimation for shaft sinking and underground cavern construction, tender design management, on-site design supervision of SCL works, and design integration for mechanical electrical works for shaft and tunnel fit-out.
Third speaker is Murchie. Sean is a chartered geologist and has 10 years of experience in the civil engineering and construction industry. Prior to joining SSE Renewables in 2022, Sean worked as an engineering geologist for Fairhurst, gaining experience in ground investigation design, management and supervision, geotechnical design, and construction site supervision across a variety of sectors. Since joining SSER, Sean has been working on the Coire Glas hydropumped storage scheme, specifically for the exploratory works. This role has involved site inspections, supervision, liaising with designers and contractors, carrying out technical designs and reviews, and management of geotechnical risk. Tom Taplin, he's a senior engineering geologist at Stantec UK, formerly working on Coire Glas Exploratory audits. Tom graduated from the University of Portsmouth with a bachelor's in engineering geology and geotechnics in 2018. Following graduating, Tom joined Stantec UK in 2019, working on several infrastructure projects as a geotechnical engineer across the south and east of England. In 2023, Tom joined Coire Glas project as a full-time site-based engineering geologist with Stantec UK, providing site support from the designer side, focusing on building the ground model and the determining requires tunnel support.
Okay, thanks. I'm getting a few messages that the online people can't see anything other than the screen. So I don't know if anyone can. That's how it is, yeah? Okay. Fair enough. Okay, so I'll hand over to our speakers. No, it's up there.
Okay, welcome everyone. This is or was Coire Glas. Anyone that's been up there will know that it always looks like that. And we've got Sean to start us off from the client's perspective of what they were after for this project.
So good evening, I'm Sean Murchie. I'm an engineer and geologist at SSE Renewables, and today we're going to talk to you about the Coire Glas hydro pump storage project and some of the work we've done to date. So as a bit of background to SSE, we are a renewable energy developer and operator based in Perth in Scotland, and we have an existing portfolio mainly of onshore wind, offshore wind, as well as an existing hydro operation across much of Scotland. We're currently developing Coire Glas, which is a proposed hydro pump storage scheme located north of Fort William, as shown on the map on the right here. It's got the potential for up to 1,500 megawatt capacity and 30 gigawatt hours of storage. So as a bit of background to the project, project site selection began in 2006, followed by planning consent, which was granted in 2020. Early design work was carried out between 2020 and 2023. Followed by the recent ground investigations that we've carried out between 2023 and 2025, which we'll talk to you a bit about today. So there's been a lot of work put into the main works design development over the past few years, including the development of the reference design, which is shown on the screen here. This is quite a good general layout of what we're trying to deliver for the works. So the key features here are the 92-metre high proposed dam in the upper quarry here, which will create this new Coire Glas reservoir. The cross section here shows an extensive array of tunnels, shafts, and an underground powerhouse cavern complex, which is located around 600 metres below the ground level here. The tunnels then connect to the existing body of water at Loch Lochy in the lower works here. So I think this diagram shows kind of the complexity of what we're trying to build. With the extensive underground nature of the works, it's also important to touch on the overall geological setting of the site. So the diagram on the left here shows a regional map of Scotland with the site located adjacent to the Great Glen Fault. Great Glen Fault is a major strike slip fault structure which cuts across much of northwest Scotland, and it's resulted in kilometre scale displacement of the rocks. On the right here is a bit of a zoomed in map showing the kind of local published geology of the site. And you'll notice two key geological domains, so to the, separated by this Great Glen Fault. So to the south of the fault, this light green colour, we have the Great Glen Fault Zone rocks, which is typically characterised by weaker, brecciated, heavily sheared fault rocks. And to the north, we have the Tarvey Samite Formation, which is more competent metasedimentary units, such as samite and semi-peelite. So there's been a lot of work, and the Great Glen Fault has been studied extensively across Scotland. But prior to the GI works, there was quite limited information on the site, which resulted in quite a lot of uncertainty over the nature of the fault zone, rocks in particular, and the position of the Great Glen boundary. So this was one of the key project risks that was identified early on, and something that, you know, this is one of the key drivers for carrying out such thorough ground investigation. So in terms of ground investigation, we've carried out two main packages of work to date: the exploratory works, which we'll talk about today, and also the wider site ground investigation. So the exploratory works in general is a drill and blast tunnel excavated from the lower works towards the proposed location of the powerhouse cavern. It also includes an underground drilling, monitoring and testing phase to acquire ground investigation data for the scheme. So the key aim of this exploratory tunnel was to investigate the ground conditions and obtain detailed geotechnical information. And it's worth noting it's quite a unique form of ground investigation, but it's allowed us to get a continuous log of data right the way through the fault zone and into the more competent units. So just to touch on the wider site ground investigation as well, we won't cover this today, but this was carried out using more conventional methods: boreholes, trial pits, geophysics, and it's focused on the kind of surface infrastructure, including the dam and reservoir footprint. So you see from the middle slide here, we've got some key organisations involved in the project today: Stantec, Covey and the BGS, as well as STRABAG and Fugro as contractors for each of the packages. So I'll hand you over to Tom now, who will talk about the design of the scheme. So I'm going to give you a very quick overview of the design of the adit. I mean, you could probably do a whole hour's presentation on the actual design, so it's going to be very brief. The design was undertaken using finite element analysis together with the Q system for a range of in situ stresses using the Rock Science RS2 and Plaxis 2D. And then I'm not going to go into the finite element analysis for this. I'm just going to touch on the Q system as it's relevant for the data collection. So we used the Q system methodology for this. It's a rock mass assessment developed in 1974. It's widely used in tunneling and underground excavations to excavate rock quality, assess rock quality and support requirements. It's based off 6 parameters. You've got your, which can be split into 3 parts. You've got your degree of rock jointing, which is your RQD, so your rock quality definition, and your joint set numbers. And then you've got your joint friction, which is your interblock shear strength. This is determined by your roughness and your joint alteration. And then you've got your active stresses, which is determined by your water ingress, and your SRF, which is your stress reduction factor, which is determined by any weak zones or overburden pressures. Our adit support system was based off of these Q values determined using geological surface mapping. However, there was a healthy amount of engineering judgment involved when doing this, because the Great Glen fault zone lacks a lot of rock outcrops or good quality rock outcrops. It was mainly done through streams. And then this range of Q values for anticipated geology was used with the tunnel proposed spans and the structure type to determine the required rock bolt lengths, spacings and shotcrete thickness. Thus providing us a full suite of support classes for varying Q values. This is one of the standard adit profiles we had. It's a 5x5 meter horseshoe shaped profile with a 4 meter adit. We had this particular one was 80 mil of sprayed shotcrete lining, and the dowels are centered at 1.5 meters, and they were 2.5 meters in length. Drilled in an array of 4 and 5. Profiles did vary with passing bays and drilling niches, so shotcrete thicknesses and dowel spacings did change. Also, the first 10 meters was a set design, more robust design with lattice girders used, and then the first 100 meters also has slightly thicker shotcrete. The range of support was from steel ribs to spot bolts, really. I'm now going to pass over to Joe, who's going to talk about mobilisation.
Nice one. So to give a bit of a roundup of how the project, in terms of the tunnel specifically, was delivered, we started off like anyone does with mobilisation. We got access to site in the Highlands of Scotland in December, which will not be missed as probably not the best time to be starting major earthworks, but that was preceded by a few months of a small ECI, but there was a real keenness from SSE for us to get on site and to get working as soon as possible. So again, we're in the Great Glen of Scotland. This is the sort of thing that we could be dealing on any given day, or even sometimes in the same day. Whether you could see the other side of the lock was dependent whether it was a good day or not. Mobilisation itself, so due to the access that we had available and the time of year, we had to be very careful with what we did. First one was a barge was used for the initial site plant deliveries, just to get us on there. The Kilfinnan Road, which comes to site, is a single track road with passing places through some tight bends and some farmland. So a limited amount of work was done to strengthen some bridges and improve that as best as could be done. But that was always a pinch point for the project. But realistically, we did manage to get pretty much everything in through that road and out again. The first works on site was felling of the commercial woodland that was around the area, giving us access basically to our compounds and the portal area, as well as some archaeological interest as well, an old sheepfold. It should be noted, RJ McLeod were absolutely vital at this point. They're their local contractor, and they really allowed us to hit the ground running. So the 3 main site compounds I'll talk about here. The first one is Area 7, that's on the left. That was our main sort of store workshops. That's where our SCL plant, provided by Cemex and supported by Normet, was located. We had the water treatment plant there from Zublin. say workshops, fabrication shops, materials storage. We had generators set up on the site to provide 3.3 kV power, which supplied to Area 7 and to the tunnel. So we were completely off-grid in the forest. We also had a magazine situated conveniently in the trees, sort of out of harm's way, and with good distances for any separation or for the capacity that we had. Coming to the portal, you'll see we were right on the lock shore there with a small line of trees in between us. That was the access to underground, right perpendicular straight into the mountain. We had a temporary spoil storage area there where we could work 24/7, whereas other areas we had restrictions, tally huts, transformer, welfare, ventilation, everything you'd expect to find at the portal. And to give a better idea of how the sort of constraints of the site really were, on the right you can see the spoil storage area. You can see how close we are to the lock. Then we've got our main site access road. The spoil storage area is on quite a steep hill. We've then got the diverted Great Glen Way footpath. So that's a major tourist route and not always followed. It would not be irregular to find someone lost wandering through site, hopefully not when anything too much was happening, into commercial woodland and then straight up to the Munro above. So we really were quite constrained in what area we had access to. I'll pass over to Tom now just to talk a bit more about the design of that spoil storage area, because that's interesting in itself.
Yeah, okay. Thank you, Joe. And yeah, thank you, audience. So Joe's mentioned already that one of the constraints on the Coire Glas works was access. So initially, obviously, they brought in material by barge, and then later brought in material by road. But it was never viable to via a single track road and an unpaved long section of unpaved road to actually remove spoil from site. Nor would that ever be a idea we'd really contemplate on this job. So what we had to do was build up a major earthwork scheme. And we divided this into two halves. You can see the constraint we had from forest to lockside, and all the material from the tunnel drive all went here. This was classified by grades, so primarily fines content, and then was distributed into two large bays or cells within the spoil storage area. The area to the south, cell A, that was for material with very little fines content. We were able to maintain quite a sharp gradient for that and maintain stability with that. But it was critical that anything going in there was effectively zero fines. Where we had fines content and when we had to deal with that went into cell B to the north, and you can see from that drawing how much additional drainage, series of cascades, drainage channels were put into that. You can see construction of cell B, bottom picture, and then the completed form of cell A in the top left. Okay, this was an ARUP design for STRABAG UK, and this was very much as the contractor managing this spoil storage ourselves. Okay, thanks.
Okay, so just carrying on, project team. So with our location and the scale of the job, we had a small team, and self-sufficiency really was the most important part of sort of working as remotely as we were. In terms of permanent staff, we had about 20 to 25 site-based personnel who were predominantly on the technical side, so engineers, geologists, and health and safety, environmental. We also were well supported from North Yorkshire, from the other STRABAG office, about maybe 15 to 20, not necessarily permanently devoted to us, but from the support functions. In terms of labour, we had 3 shift teams working on a 12-hour back-to-back rotation. We did a 10-5 rotation with them, owing to the site location, commuting distances. About to have 1 long stretch and then 5 days off in a row, just so people aren't spending their own times travelling. On each shift team, 8 tunnel ops, mostly made up of your pit boss, drillers, shot firers, sprayers, and then 4 fitters and 2 electricians per shift. Additional permanent days crew were there responsible for the road maintenance, running the stores and overall supervision. And again, RJ McLeod basically ran the muck shift. So we transported all spoil from the tunnel to the temporary spoil storage area, and they were responsible for taking it up to the main spoil storage area and the construction of the spoil storage area itself. Okay, on to the good stuff. The first blast was done in March 2023. This was for the portal, so this was a surface blast. The results speak for themselves. I was expecting a little bit more of a reaction, but anyway. Those will have noticed the first part of that was a pre-split. That was really effective at giving us a really clean joint to break back to. You can actually see from the bottom image there, the half barrels are still showing there. That was really effective. And with actually Tom Woods in the audience there doing a bit of surveying for us. Above the portal, we had soil nails in some of the weaker ground, and below a bench, we were into rock dowels. And then there was a set of horizontal spiles built in basically above the portal for protecting those first two advances. We then added to that as well a false portal. So as already mentioned, the first 10 meters was done with lattice girder support. So we built effectively ring zero inside of the portal, giving us the ability to connect onto that lattice. So we're already working off something that was set out into the correct position. That was then sprayed in, and we had the inaugural breaking ground ceremony with Father Danny from the local church. Very keen to get the local community involved with what we're up to. So yeah, that's breaking ground there with the Shafe excavator, which basically took us into the tunnel construction period of the project. So we started just ahead of program on May 23, and we had a bit of a soft start, which was really useful basically to make sure that all the equipment was working. We had a bit of a gradual ramp up in production, so it wasn't a mad dash to start, and any teething problems basically came out through that. We've seen the cross section, but this is the long section that we were dealing with. So it was 900 meters long. We had passing bays roughly every 250 meters. Generally, it was quite straight, and then we went on to a slight sort of long radius right-hand bend. So those passing bays give us logistics of the turning circles, and then we had the drilling gallery at the far end. Vertical alignment, first 100 or so meters was done quite steeply at 7% grade, and then after that, it was a 4% grade right down to the drilling gallery. So for those not familiar with drill and blast, we'll just do a very quick run through. But basically, each advanced cycle, and we'd normally do 2 of these per day in a standard section of Class B tunnel, say, start off with drilling, a bit more on that in a second. We'd then charge that, also some more details on charging in a second. We're using cartridge emulsion, which is sort of the easiest thing in terms of procurement and use, given the length of the drive. We'd then blast. We needed between half an hour and an hour to allow the fumes to clear, depending on the length, and we'd go in and muck out that drive and that advance. Scaling in this ground and hard rock was some of the most important part of the process, and that was especially important with the blocky ground that we were in. We then had an hour dedicated to the mapping. Tom will mention more of this on this later, but this was one of the key parts of the project. That would probably make most pit bosses livid, the fact they know they've got a geologist unmovable for an hour to look at the face. But I say on this project, it was a very specific thing. Spray was then completed, so sprayed concrete to the desired thickness, and then we go supports depending on what that mapping had told us, and we'd repeat the cycle again. A bit more about that support class system as well. So we've seen the design, how that would actually work on site. We'd have the daily review meeting. We would get the design for the upcoming section of tunnel. We would sign off as required, a required excavation support sheet. That is something that everybody that needs it, engineers, geologists, pit boss, can have in their pockets. And it's going to tell them basically for what the information the geologists provide them with, what support they need to install. The mapping's then completed. That comes out with that Q value, and the support can be decided. But there's also elements of flexibility built into this system. So there's toolbox measures put into that res if we encounter water, if we encounter blocks that look like they're a wedge feature that can't be scaled, all sorts of things. And this is an iterative process as well, which is good. So features that we encountered throughout the tunneling, as we went on, if we found solutions that were better at dealing with them, we could put an RFI in, we could build that into the res, and then we've got the best toolbox basically to deal with the systems and the issues or just the ground itself. Very quickly, equipment. So we're using an ITC Shafe with a 5-ton mini digger as a backup, Epiroc Boomer S2 drill rig. We had a Norma Eliva fully electric, I believe the first fully electric 520 in the UK, plus a backup 503 and pump. GTA was a heavy-duty lifting basket. Dici dumpers will be familiar to most, and then a front-end loader for the surface and for cleaning up the muck pile after the blast. Some of the good software I had available. So the Epiroc Underground Manager software was really useful. Basically, rather than setting out a profile on the face from a total station, what we were able to do, set up a laser line to the side with the total station. The arm on the boomer could then be sighted on 2 targets onto that laser line, and the rig would know its position in the tunnel in space. You tell it which drill plan you want for that section of tunnel, and it'll know where the hole positions are. Really useful. Blasting, I say we were using conventional emulsion explosives, cartridge emulsion. We were generally drilling a 3-meter advance, which requires about 70 holes, 66 charged, 4 void. We were using about 160 to 180 kg of cartridge per blast, and then it was a shock tube initiation system, so 6-meter lengths to most of that in the hole, followed by bunch connector, surface connector, and electric deck to set that off. And if it all went well, it would look like this. Fragmentation was one of the most important things for us. Timing was everything. We didn't want to spend time breaking apart loose blocks and large blocks. Everything had to get the apron of the chafe. So those that know their powder factors might have thought we were probably overblasting a little bit, but I say time was important to us, and getting it up that chafe as fast as possible was quite important. We did some more clever blasting as well. So that's the setup for the smooth blast we did later on in the project. We also did, that's from a wedge cut when we were blasting out to enlarge for a passing bay. So wedge cut in the center, and then we're able to do quite a long advance, 2 of those in, and then we could start slash cutting on the side down to provide us with a widening. Towards the end in the drilling gallery, the blast got a lot bigger. By the end, we were sort of setting off about 360 kg of a cartridge per blast. By the time we got to the real drilling gallery sections, 5 bunch connectors, you know, some good blasting. Profile control, again, we had some good software available. Amberg was really useful to us. We could basically build the tunnel in the software. Engineers for the chainage of the tunnel knew what the profile was. We could do as-built down there at the face to make sure that everything was in tolerance in terms of profile, check it again after the spray, and make sure we've applied the correct thickness. And then all of those records form basically our quality records for the job. That's all very well. That was basically building the tunnel, but actually, as Tom will say, that wasn't the most important part of the process.
Yeah, so for the most important part and the real reason for the edit, the geological deliverables and processes, mapping was undertaken at each advance. And it was an hours long between both the contractor and the design engineers. As you can see, you've got 3 mappers there. So we'd each do the mapping separately and then come together afterwards and discuss our findings and come up with a Q value together. And then that provides the support class for each advance. And then following the mapping, each of us would have our own proformas to fill out. As you can see on the right-hand side, this is one of ours from the designer side. This was all done online through ArcGIS. And then each performer would then be discussed in the following day's DRM, signed off, and the support class approved. If any further spot bolting or anything like that was needed, then it would also be signed off in the DRM. And that's just another example of one of our mapping sheets. That's for a drilling gallery. You can see you've got a nice felsic intrusion cut across with a discrete fault there. So we also produced this geological long section for the full scheme of the tunnel. So the mapping from the crown and the walls all went down on one sheet, and we use this to determine reoccurring joints and determine where fluctuating joints were as well. It helped us understand dominant joint sets across sections of the tunnel, or particular geological features, or where we had tunnel structures for potential problematic joint sets. This section was fairly early on in the tunnel, in the cataclysite, which was fairly difficult to map, hence why you've got heavily jointed and varying jointed sets. Then we had the advanced probing. So probing was undertaken approximately 20 to 25 meters in advance of the tunnel. 2 probe holes were undertaken to provide an idea of what we were to expect when it comes to blasting. Green is good ground, where sort of drilling was slow, and then red is poor ground where drilling was slightly faster. Data was collected from the boomer on 20mm increments, measuring the drill length and the time.
to provide us with a penetration rate. The graph on the right shows you the difference between the two arms on the boomer. The peaks on that are actually where they've changed the rods, so it's actually a fairly consistent drilling penetration. Similar to the probing, we also use measure rod drilling data to give us an idea of where we encountered some soft stuff. So you can see on the right hand side there where we hit the fault, which
Fascinating.
spoken about a bit later.
Phew.
The red
That's engineering and a half, that is.
show us poor ground.
Right.
This was all well and
Are you
good,
doing
but the drilling data was,
NFL?
well, the material had already
do we
been
have
blasted
in?
by the time that you'd
My
been able to look
word.
at it, because it was
That's
only 3
rather
months
nice.
of drilling. So yeah. And then while we were mapping, we were doing the LiDAR and the photogrammetry,
table.
sorry. We use this data
Okay.
to correlate with our map joint sets that we picked in person. And we use the LiDAR data in a piece of software called MapTech. That allowed us to both manually pick the joint sets and automatically pick joint sets. This allowed us to collect much more data, more measurements of dip and dip directions of the discontinuities, also more
Doing two
accurate
things.
measurements.
I'm listening to
due
you
to us
trying
when
to
we're
and
mapping,
listening
we're
to a
sort of 3
lecture.
meters away from the face. However, the only downside to this was heavily dependent on the quality of the scan. If the scan wasn't particularly good, then you couldn't pick anything out. Then the uses of this LiDAR data. So we used the Rock Science suite. We took this data and input it into Rock Science dips, and we pulled out our dominant joint sets. And then following that, we would use the Rock Science unwedge to determine if there's any wedges in our advances, and if our prescribed support was suitable. If not, then we had to install further rock bolts. The section on the right hand side, we found a wedge that wasn't quite meeting the right factor of safety for us, so we had to install an additional 3 7-meter rock bolts into the crown due to the persistence of that single discontinuity. Now I'm going to pass over to Joe to have a chat about the SQ and the fault zone.
So we told
My camera came on in
until,
the beginning of the
November
presentation. I
23
was like,
into December.
I didn't
and,
switch it on. No,
At this
I
point, we
switched
sort
it
of came
off,
across
and then they switched it on
what
themselves.
happens when
They put it on that end.
you go looking
I must
for
go
interesting
in
geology.
as a host or
So
speaker.
Advanced 282, you
It
can
recognised
see
me as
up
a
in the
host or
top
speaker.
here, the start of a feature in the crown,
I know.
competent rock underneath,
Picking my
and then
nose.
this
Is
is fault gouge.
that was
So,
scary.
my geology knowledge is not as good as the others, but realistically on the next
It shouldn't
blast,
happen.
we could see very clearly that what we were
Well.
into was bad, very poor quality rock. We had about 1.5 meters of overbreak above this. Actually, when the face mapping was done for this advance, we'd already decided to get in and spray it, or at least the poor material, just to get it closed as soon as possible. But we were no longer in good, competent hard rock. We were at an overburden of about 420 meters at this point, and we'd also started widening into the next passing bay. Q was right down low, much lower than some of the other advances. We'd hit discrete faults before, and there was a hope this would be the same. So there was the agreement to do a short advance, a little more than a meter, and hopefully see some improvement in the crown. But after that blast, we could see that this material went straight up to the top, and basically left us in the situation with poor ground, and we're out with basically the design parameters. The face mapping shows it just as clearly. I like the note up here that says fault material not affecting stability in this advance, but we can see that it only got worse. Credit to Antonio for these ones. We managed to do some investigations on the ground. We had the probing basically of access to us. We probed behind us and in front of us. We were able to sort of map out the location of the fault. This sketch is lovely. I think this is one of Rob's. Forward of us, whenever we hit the change in color, basically we were aware we'd hit basically this faulted material. We went ahead of us, perpendicular to the inclination of the fault we'd been able to work out, and we were still not seeing any improvement. So that left us basically, I say, out with the design parameters. The Class D design only worked for an overburden up to say 400 meters, and basically the decision was then taken to abandon the passing bay, relocate it, and I'll let Sean run through what we then did as a project to basically get past it.
Yep, so as Joe says, the ground conditions encountered here were out with the design parameters for the original design. So we instructed a halt to tunneling at this point, and we instructed Stantec Covey to develop a bespoke design to allow us to continue the tunnel safely. So it's worth noting that Stantec Covey carried out this design with very little information, mainly based on the face mapping records that have been encountered in the main part of the fault zone, as well as the additional probing that Joe's just shown there. In terms of the design as a whole, it was more based on numerical modelling, as well as the application of the geological strength index as opposed to the Q system, which had been used for most of the other tunnel. So this was a really good period of collaborative working between SSE, Stantec Covey, and STRABAG to kind of optimize and refine this design as well, through several technical workshops. You see in the middle of the screen here, this is a cross-sectional profile of the new support that was installed. So the key features are this obviously circular profile changing from the original horseshoe shape. And this is formed from a steel ring, as well as 300 mils of shotcrete sprayed around that. We have a series of radial dowels surrounding the circumference of the tunnel, as well as spouls in the crown and face support in terms of face dowels to give extra support during excavation. So in addition to this, the support leading up to that fault zone had already been installed through shotcrete and dowels. And Stantec Covey has also demonstrated that the fault plane was likely to dip just above the crown in this area. So the face mapping was showing generally okay rock, but there was also a risk that there was poor ground just above the crown and insufficient good quality rock cover. So with this part of the tunnel over a length of maybe 7 meters, I think, we asked Stantec Covey again to produce a bespoke design in this area in the form of reinforced steel ribs and added shotcrete. So it's got a funny profile here on the image on the right, and that's where we've kind of expanded out and widened for the passing bay that was originally proposed at that location. So I think from our point of view at SSE, this encountering the fault zone did result in a delay to the works, but it's something that we're really happy that we've identified during this exploratory tunnel. We've pinpointed the location of it and characterized the nature of it as well. So we see it as a positive, taking that into the main works.
Okay, thank you, Sean. So one of the things we were able to do during this stoppage while we were redesigning the tunnel to advance through is some quite good ground investigation. So the purpose behind this was to understand the fault zone, verify the design assumptions. Design assumptions at this point were actually progressing at some pace, and we did this in two main ways. The first thing we did almost immediately after stopping and forming those Norwegian rib advances was to carry out a tunnel seismic survey. So we brought in a company called Amberg to do that, and that survey really gave us estimated the extent of the fractured ground by a non-intrusive method. So what we would be able to do after that is determine what additional ground investigation works we could sensibly do within this stoppage. And the other main thing we did during the stoppage was drill a horizontal borehole. And we did that in the direction of Tunnel Drive. The idea behind that was to estimate the thickness of poor ground. You wouldn't necessarily be able to estimate the true thickness of a fault, but ultimately that's more of an academic exercise compared to the zone of poor ground, which you would see very, very clearly through the geotechnical log. I'd say the mobilization for this was certainly for the Amberg TSB was extremely quick, but also for the drilling. So at this point, we were expecting to mobilize for the main tunnel GI early in the new year. So we actually brought forward our drilling subcontractor. So we're very lucky to have a group company, Zublin, as our main drilling subcontractor. We brought them forward, and we were able to carry out the horizontal borehole during the design phase. And I'll let talk more about the design of the SQ.
So when it actually came to getting through SQ, we've seen the cross section in 3D. That's the sort of level of support that we were dealing with for installation. But as Sean's already mentioned, thankfully at this time we also had the ability to make some optimizations that weren't going to impact the safety, or in fact improve the safety. But basically, because we had the abandoned passing bay in that zone, we actually had quite a large space to deal with. And that actually allowed us to do some horizontal spiling rather than the overhead spiling per advance. We were able to couple the drill rigs, so we could ended up doing about 12 meters of horizontal spiling ahead. And that meant that generally staying outside of the profile, we had that overhead protection that was much easier and much faster. And again, getting through the fault zone quickly was in everybody's best interest. The limited time for open ground was really important. What that actually looked like in the end, you can see on the left there the number of profiles that we had. The first was the normal tunnel alignment. We then brought it to the side 1 meter and eventually down. And you can see the blue and white markings for the spiral positions. We also, to restart off tunneling after, again, a few months of no activity, but again, over winter on site without tunneling happening, we wanted to make sure that we were fully ready to restart. We did 2 pocket excavations either side of the face, which allowed us to site the first leg of a H-beam, and then that allowed us again something to work on to connect that first advance. You can see there that the overhead spirals were quite effective. They limited that overbreak. It couldn't get that much higher than the spirals, and yeah, had a limit of overhead protection for the guys that were working in that area and positioning those ribs with realistically, a small amount of shotcrete, but yeah, overhead spirals to make it a lot safer. Other things quickly to run through, the shape we were using at that point, given it had the apron on the front and we were now going to top heading and bench excavations, we ended up getting in the Terex 210 for this area. You can see from the space proofing that was really well suited for the sizes and the area we're working in. You get an idea of the amount of support in each area from that central photo. You've got the H-beam ring going full circle. You've got dowels in between. You had the overhead spirals. This was really heavy. It was soft ground tunneling works basically in hard rock. As we went along, the ground improved. We were able to drop the bench level quite quickly from being a half-height bench to a horseshoe, which eased basically the access and the space we had available, and also that sort of working at height from a high bench and then having a lower one. As things improved again, we actually resumed blasting, not with any great amount of powder, but it was, with spacings quite wide, about 1 meter, we were able to fracture that face quickly and then just basically finish it off with a road header. So yeah, in the end, we installed 28 meters of Class SQ, completed in 1 month. So we averaged just over 1 meter a day through that zone, which I think was very impressive given some of the initial, what we were looking at the start and some of the advance rates that we thought we would be dealing with. So yeah, that took us into the fault zone to the end of March 24. And yeah, at that point, we basically had what we thought was the home straight to the drilling gallery. And I'll let Sean take it from there.
So yeah, spring 2024, tunneling was going pretty well, but to provide a bit of more context to the overall project as a whole, data was being reviewed and assessed from the exploratory works in real time effectively and used to verify against some assumptions for the main works reference design. So with that in mind, we're really happy with the quality of the data that we're getting from the tunneling and instructed an extension to the tunnel. So this resulted in an extension to the tunnel of 300 meters. It also resulted in the construction of 2 additional drilling galleries. So you'll see from this diagram here, we're tunneling at greater depths than originally planned. And also there's a slight change in alignment. If you look at the diagram on the left here, the tunnel kinks round to the right in the northern part of the tunnel there. And that's to kind of curve around the side of where the proposed locations of the caverns were to be sited. So in addition to this, there was a change to the underground ground investigation works. So the original scope on the left-hand side had 1 drilling gallery and a series of boreholes drilled from that single point. With the new alignment, we obviously had 3 drilling galleries, and so we were drilling from multiple points along that extension. And from our point of view, this increased spatial coverage of the data, as well as being able to carry out in situ testing in closer proximity to where the caverns are. And at more representative depths. So while these 2 changes were quite significant, we're happy that we kind of maximized the data quality, particularly from the tunneling here.
again, just to talk about the delivery of that, although it came as a bit of a surprise, we got a very clear instruction from SSE basically that they wanted this extension. We didn't know exactly what it looked like at that point, but they gave us a clear instruction, basically keep the people on site, get the materials and equipment you need and get it done. So we were aware that a lot of it was going to have to get worked out along the way. For a long time, the whiteboard on site was the most up-to-date design information we probably had. And we were literally sometimes building or getting the information on a Friday afternoon for what we'd be building next week. It didn't help that April was our biggest month of production just before the extension. So we got to it very quickly. You can see from the center here, these are the three galleries, gallery A, B, and C. Every different color is a different profile. So these sections were complicated in the profiles. We needed higher profiles in some places to enable construction off to the side. We had the testing niches to think about, which were a different profile again. So it was a complicated bit, but I just think it was a fantastic example of the collaboration, you know, building on what we'd had to work through with SQ. We were able to work quickly. Everyone needed to understand each other's constraints in terms of, you know, there's things like electrical supply that become really imperative to actually enable you to build the next section of tunnel. But yeah, we also had changes in the a tight radius bend, which became, you know, basically the limit of what we could build and how tightly we could go, and changes in vertical alignment. But yeah, you can see from some of the photos, we were really into some of the largest spans of the time. You know, they're 8 meters wide by 6 meters high. The biggest hurdles for us really with a tight time frame was the procurement of the explosives. I mean, they're not an off-the-shelf product. Our suppliers, Brexco with Austin Powder and Orica, they did fantastic work for us to get some of these, you know, detonators at the front of the queue and into the country from Europe. Otherwise, we never would have been able to proceed. Other things like the refuge chamber we'd never needed for the works before, but because we were now going to be doing a GI works with 2 open faces, or 2 drilling faces, that is, we needed a refuge chamber so that people could work in by of each other, and that had never been envisaged. So again, things had to be bought quickly and get to site as soon as possible. Labour was all signed, sealed to go off to HS2, and we needed to pull them back and say, no, we need you for an extra 2 or 3 months. But anyway, the last blast, 502, was done on the 1st of August, 24, and that was only 3 months after the extension had been instructed. So, you know, we built 3 galleries, 200 meters tunnel in that short period. So by that point, things were really up and running. I'll pass back to Tom to again talk about more of the GI and what we got at the end of the works.
So there's a GI summary. As you can see, 75% of the installation of support was the Class B or a Class B variant. Very little was Class A. We did have some material that possibly could be Class A, but we decided with the option of Class B2, which was slightly lighter touch than Class B. You've got your 2% of the SQ, which Joe's spoken about, 1% of Class C, which is your first 12 meters, and then the remaining is niches and passing bays. So as Joe said earlier, there's a total of 502 advances mapped for the tunnel construction, about 5,000 rock dowels installed, 4,500 meters cubed of shotcrete was installed over the whole thing. Then this is our measure whilst drilling summary. So all of the data pulled from the probing and the blast holes just gives you a good idea of where we encountered some poorer material, especially just after that passing bay 3, which is where we encountered that fault zone. And then right at the start as well, some slightly poorer material. Water summary. Thankfully, we didn't encounter water that much. No major issues. Recorded 9 advances where it affected the Q value. And even then it was sort of measured as medium inflow, so like a sort of a rain shower sort of level. And the permanent weep holes were installed at 6 locations, 3 of which were very close to each other. We reckon that's likely connected through discontinuities through a stream above the adit. I think there was around 300 meters in. All of this was managed through drainage channels in the invert and then pumped out to the water treatment plant. The worst case was a 30 litre a minute inflow. But yeah, it's all good. Most of the probe holes were dry. There's a couple of probe holes where water sort of was encountered, but it was always sort of petered out within the hour, so it didn't really stop progress. Just a couple of videos of water. So you can see on the right hand side, that's the probe hole. That didn't last very long. That was so about an hour. I don't know if then you can sort of see shower light from the joint set on the left-hand side. And then we've got the LiDAR fly-through. So obviously each map in advance, there was a LiDAR scan. As you can see, we go through this. It was all measured at 1 millimeter scales. And you can see the excavation profiles. You just pass through the first passing bay. And then you'll see sort of as we get past the SQ system, there is a notable difference in the quality of rock. You can see it is slightly more blocky. I'll just let that run out as you coming into passing base 3 just now, and then very quickly into the SQ section, and then it sort of starts to get much more blocky around now as you pass into the first drilling bay or gallery, and then into the second before you get to the end of the tunnel. Pass over to Tom for the underground GI.
Yeah, okay. So one of the things which that LiDAR survey really shows is it gives a very, very good meter by meter record of, gives an incredible density of data. And Tom certainly stole my thunder earlier on when he said that the tunnel itself is an incredible form of GI. While that may be true, what it doesn't do is give us the same predictive power as a series of boreholes do. So what we did as Sean said, this design was quite dynamic as we were progressing to each of these drilling galleries. But what it allowed us to do was consider the construction requirements and the operational requirements for that underground ground investigation work. So the logistics of bringing in drilling equipment, it opened up the opportunity for simultaneous drilling operations in different drilling galleries, simultaneous in situ testing, and drilling operations as well. Overall, we were able to carry out a underground ground investigation campaign, which has been one of the largest and most complex in the UK in recent years. So this was completed between August and December 2024. A total of just over 1,300 meters of wireline core drilling was carried out across 8 long exploratory holes, the longest being 285 meters horizontally, and a total of 415 meters of conventional core drilling across 23 shorter holes. And by short hole, I'm talking up to 84 meters long. A wide range of novel techniques were employed, especially with respect to the geophysics and in situ testing. Many of these holes were at very, very shallow inclination, or indeed upwards inclination. That's not conventional for ground investigation at all. So, okay. One of the primary components of the underground ground investigation was the drilling and logging. So core drilling was carried out by our specialist subcontractor Zublin, a group company who carried out the drilling for the SQ works as well. We generally use wireline double tube drilling at CH96 or HQ size. So that's, for those of you who understand ground investigation, that's quite a small core size compared to what's normal, which is GeoBoreS for a vertical hole. And we use specialist electric hydraulic rigs, which were capable of drilling at any inclination. That was an important part of this GI because so much of it was a very shallow angle. Core logging, that was done by the STRABAG UK team. So that was done within the drilling galleries, and that was deliberate to avoid any damage and minimize the amount of transport and damage to the core before we logged it. Ultimately, we spent an awful lot of money getting the tunnel to this point. We've spent an awful lot of money drilling cored holes. We want to be able to log this. We want to be able to log the in situ conditions without damage to the core. Okay, I'll say a bit more on the in situ testing. first to say we carried out a large number of quite varied techniques. Okay, the in situ testing was carried out for three main reasons. First of them was to determine the ground composition, the structure of a borehole. Our primary tool for this was wireline geophysics and televiewer data. Again, because of the inclination of some of these holes, we had to come up with novel tool pushing techniques. Normally, this is lifted up on a wireline winch on an A-frame. We were pushing in the tools with the drilling rig and then pulling them out with the wireline winch. That's not normally done. We also carried out tests for in situ strength. We did three main tests for this. One is a Goodwin jack. That's a tool. It's an older method designed really for hard rock, which we had. We used a high pressure dilatometer, which is generally designed for softer rock, but we actually carried out to probably its operational limit. And we did a plate jack. A plate jack test is quite a simple concept. You push apart the tunnel sidewalls with a very large hydraulic ram, measure the deformation of the sidewalls very accurately. That required an enormous amount of temporary works. The smooth blasting, which Joe mentioned earlier, and preparation of bearing surfaces as well. The final set of tests we carried out, situ tests we carried out for the underground GI, were to measure in situ stress. Now, Sean and Tom will tell you that this is an extremely important parameter for design of an any underground excavation, but particularly a large underground cavern or a powerhouse cavern. For example, we did this in two main ways. We used a technique called hydrofracture, which, as the name suggests, you're injecting water at very high pressure into the ground. You're inducing a fracture within the rock, and then you're measuring the stresses at which that fracture closes. That gives you an estimate of both the direction and magnitude of the in situ stress. Because we had a tunnel there as well, we were able to use a technique called overcoring, which again provides a lot of redundancy in measurements of those in situ stress. What you're doing there is you're gluing a cell into the rock and then overcoring it, releasing that stress and measuring how that stress changes. Okay, what I'll do is I'll hand over to a brief summary of the project in numbers.
Okay, I think we've mentioned many of these already. In total, totting up all the numbers, including niches, we did just over 1.2 kilometers of tunnel in the end. Excavated volume that had to go to the spoil storage area was just over 38,000 meters cubed. 80 tons of explosives, 43,000 detonators. We've said already, a lot of sprayed concrete, a lot of bolts, 500 blasts, and between Doug and myself, I think we did 455 tunnel inductions over the length of the project, as much as it pains me. Project progress data. So this data is great because we're able to dig into some of this for some of the future projects hopefully we'll be involved in. You can see the tunnel breakdown. I won't go into this in great detail, but basically that's the breakdown of all the advances, and thankfully not a massive, a huge delay wedge there. Month on month, although it doesn't quite look it from the graph above, depending on exactly what profile we're in at the time, we generally achieved a month on month improvement on advance rate throughout the project. So we were only getting better. I say after Class SQ, the guys were like a coiled spring, and they put in 153 meters of tunnel in a month, which was averaging more than 5 meters a day, which is pretty fantastic. Other achievements, just to blow our own trumpet for a bit, you know, if you've been to any of the awards ceremonies recently, there's always a Coire Glas representing party. Yeah, this is probably one of the biggest drill and blast projects in the UK for recent decades. Upskilling people is probably the most important one. Coming into this job, skill shortage was a real issue for us, so we've put a lot of effort into there. We've got another 10 qualified shot firers at the end of the project. Hard rock SCL, you know, a lot of SCL works happen in London, but hard rock SCL, so especially the drilling for that was very important. Face mapping, actually finding geologists with sufficient experience in hard rock face mapping was not easy. And again, now there's a lot more core logging as well, should be thrown in there. Engagement with the local fire and rescue service. So there's another big project on the horizon here, but we were really glad that actually the local team could support us for the works we did, you know, for the limited works realistically compared to the main works, but we didn't have to have our own dedicated team. They were there with us, should say as well, LBA, their fire risk assessments, and getting all of us together in a room for that to make sure that was demonstrable was really useful as well to keep us above board. Successful blend of national, international, along with the local workforce as well. One of the biggest ones was, despite the hurdles that we've gone through, the collaboration between the client, designer, and contractor, I think, is exemplar here. Like, we are able to do this talk. We're all still friends. So, and after some of the hurdles, some projects might not manage that. Innovations, there's a lot of stuff that we could talk about here. Some of it's been talked about already. Tunneling for GI in itself was probably the biggest innovation, but we've spoken about that at length. But it's obviously proved really effective here. The information they've got for the main works is fantastic. The BGS have been involved all the way as well. So that knowledge is not being locked away. That's able to update sort of wider geological knowledge. Smooth blasting, the methods we used here weren't really that applicable for overbreak control, but for the main works, this is fantastic. You know, when we're really looking to reduce the size of or reduce the overbreak, we've got techniques that we know now work in this geology. Tom's already mentioned innovations on underground GI, the spoil storage area used to limit the wastage and not cause any disruption. You know, all that muck that could have gone along that local road, that's still on site and is available for the future works in the area. The first use of the Amberg TSP, that was on this project. And the LiDAR, although mostly a underground GI tool, actually afterwards, it's been so useful for us for providing as-builts, for looking at data, for basically being able to look back on an accurate, millimeter accurate as-built of the entire tunnel stitched together. Health and safety. The biggest health and safety thing we're monitoring here is the ground itself and controlling that, but there's a lot of other things we could be talking about. Again, we've managed over 500,000 man-hours and 2 years have gone by since the last LTI. We've had a good engagement with the HSE who've been on site, lots of health monitoring done. Environmental, on a site like where we are, we've had to be very, very good. Dan Arnold, our environmental manager, deserves special credit for his work with SEPA in the early days and then monitoring us throughout the works. Blast noise has been a key one at the start, and then nuisance noise after that. We've had 17 PMO visits without any non-compliances. There's a lot of good work there. Local stakeholders as well. So we've had the Highland Council, SEPA, Nature Scott all out to site. There's going to be a lot more work like this in the Highlands, and we've been able to show them a little snapshot of what it looks like. And now I'll hand over to Sean to talk about, most importantly, what's next.
So yeah, we've done some fantastic work to date on the project, but there's still quite a long way to go in terms of the main works. So we're currently waiting final investment decision from SSE. This is heavily linked to the confirmation of the cap and floor support mechanism, which has recently been introduced by the UK government and Ofgem. So following this, there'll be a period of engagement with designers and contractors to finalise the detailed design of the scheme, followed by construction, and we're hoping that we can get the project completed in the early 2030s. So yeah, just to say, obviously this screen shows the amount of contractors, subcontractors that have been involved in this project to date. So we just want to say thank you for your support and the part that you've played in this really unique project. And thanks to the audience and those that have dialed in online. We're happy to answer any questions.
Okay, thank you very much. Yeah, there's seats down the front if anyone wants to come down. Okay, do we have any questions?
Mike McConnell, retired Balfour International. Congratulations, guys. I think a four-person presentation really demonstrated that I think you must have been working with a very good team on site. So I think that was a nice first for BTS here to hear the presentation like that. I think just one of my points is you were demonstrating the exploratory tunnel being a horseshoe 5 meters by 5 meters. But obviously any hydro consists of surge chambers, all sorts of ancillary access roads, and high pressure, low pressure tunnels and everything. And were you then able to actually do your SI covering all these other underground elements from that drive that you're primarily pushing through?
So I think, yeah, obviously the reference design is the preliminary design at the moment, and the detailed design of those tunnels will be refined based on this information. Yeah, I think this tunnel has excavated in one alignment and got really good information at that particular site, but we recognise that the tunnels and there's different shafts in various places that might have different ground conditions to that. But I think, as I touched on at the start, we have carried out the wider site ground investigation as well. Again, covering a lot of the deeper shafts and the surface works as well. So yeah, we're confident that we've carried out as comprehensive a package of ground investigation as we probably could do at this stage. So that's to be determined at the moment. This is kind of the main package of work that we've carried out today. So yeah, that'll be any additional SI will need to be determined later on.
So if I could maybe add to that, there was quite an elaborate 3D model produced on the back of a wider site SI, so the surface SI, which informed a lot of the decisions for orientation of underground drilling as well. And that was quite an iterative process as well, based on what we encountered in the fault zone, and that changed throughout the GI. So it was very much looking at what we found and how do we get the best data possible from the underground works.
Hi, it's Claire now from Mott MacDonald, and it's a bit of a continuation to that. Because you presented the fault, and I wondered if that was anticipated to hit anything critical like the powerhouse cavern or headways tunnel.
I'm happy to say that. So what I would say to that is that the ground modelling and the sort of assessment of the data is still kind of ongoing. Yeah, I think there is a fault there, and we know about that, and we can kind of model that in terms of the overall project. But what I would say is that features in terms of the design will maybe move and things for the reference design. But that's again one for the detailed design phase.
Chris Shue, Atkins Realis. Can I ask two questions? But first question is, are you doing long-term convergence monitoring for the rock to see whether it's still creeping? First question. Second question is, if in the SQ section, if you didn't support it immediately, would the material just simply unravel to the surface?
If I take the first one, yes, we did the quarterly monitoring in the tunnel just last weekend. So we didn't actually mention this during the presentation, but obviously during the excavation, we did survey arrays at set frequencies, depending on the ground conditions, generally every 20 meters. They'd be monitored every day for 7 days, and then weekly for 3 weeks. And then providing everything was above board, that would then drop to monthly for the length of the excavation works. And then now we're into the maintenance phase, that's dropped now to quarterly. So yes, we are still doing some monitoring, very limited. Realistically, other than in the fault zone, we've seen by the time the monitoring was installed, which had to be realistically 3 or 4 blasts back, because monitoring doesn't respond very well to being blasted with 150 kgs of explosives. By the time we've got that array in and we start monitoring, we were seeing negligible movement, and that has continued. But in the fault zone, you can definitely see that before we closed the inverts, there was 2 or 3 millimeters of convergence in especially the legs. So there was movement, but in the good rock, it was very good.
Okay, we'll take one online. And could you drop the spotlights a little bit, please?
So there is a question online asking, at any point during the tunneling, were there concerns about tunnel collapse, and how did you manage the risk, and if you implemented any monitoring schemes?
I'll take that one as well. During the works, I would say up until the fault zone, nothing that we hit, we didn't feel like we could deal with the toolboxes that we had. But that's everyone's opinion. I would hope as well. At the fault zone, genuinely, you know, we were in a very poor area of rock, and yeah, the initial support that was put in there on finding it was very robust, but evidently had to be bolstered up from the designer's work. But I say generally, the ground conditions are very, very faulted. The support we were putting in with the rock bolts was very effective. I wasn't worried, so.
Yeah, me neither. No.
Okay, any more questions out there? One at the back there. Yeah, at the back there. There you go.
Adilo Bangbade, Stantec. Two simple questions. What does SQ stand for? Maybe I didn't hear it. And then the second one is what happens to the tunnel in the long run? Do you just backfill it or?
Who wants to take SQ? I don't know. We've been trying to guess for a long time.
So SQ is one of these things that just kind of stuck with the design.
We've got some ideas.
Yeah, in terms of the long-term future of the adit, so we obviously have a tunnel there. It's hopefully going to be used as part of the access for main works construction at the moment. So that's the current kind of idea that we have for that.
It's worth saying, you know, we are a stone's throw already underground from the three main underground structures. So yeah, it's not hard to see how that could be, it's going to be very useful when we get to that point.
Okay, another question? Yeah.
Paul Perry from AECOM. Why did you choose a horseshoe profile when previously most of the hydroelectric schemes by Scottish Hydro were D-shaped? I just wondered if there was a particular reason for that.
I'm not aware of the reason why we used a horseshoe. The designer is sitting in the room, so you could have a conversation with him after this.
We'll set you up.
Sorry, Rob.
All right, another question? Yeah, over there.
Hi there, Sam Theophilus from Hockteeth. I'm just wondering about the boreholes, why you went for the reduced diameter, and then as a follow-up to that, if it affected the laboratory testing you could complete on that reduced diameter.
Yeah, so the borehole diameter is constrained by the size of rig, and as I said in the presentation, normally for a vertical borehole from surface, you'll be looking at generally geobore S type size. That wasn't possible with the equipment we could bring, which was suitable for doing the drilling from the tunnel. So it was considered that HQ was a sensible size for considering the entirety of these boreholes were in hard rock. So that was a decision made quite early on in the specification stage. What we did actually change from a general assumption of triple tube coring to double tube coring once we demonstrated the quality of the rock conditions, quality of the core we were getting out. So yeah, in answer to the HQ point, HQ was the largest size we used as well outside of the overcoring. The overcoring required special conventional core barrels to be used with those rigs. Trying to get a wireline system with those rigs at larger size wasn't viable.
Okay, one online, Arabelle.
Yeah, there are a couple of about the GI outside. So they are asking if the GI outside the tunnel carried out by Fugro play a part in your progressive decisions inside the tunnel, but also was the fault zone you encounter in the tunnel as thick as you could determine from the surface mapping based on the boreholes?
So yeah, obviously it was a separate package of works. I think the designer was aware of the data that we're getting from the wider site GI, which probably influenced their sort of thinking, I guess. And again, it was data coming in live, being reviewed and assessed in real time, really. And your second part was about the
if the fault was as thick as you thought from the boreholes.
As in the underground borehole or
From the surface, they are.
the surface? It wasn't encountered in any boreholes from the surface.
Okay.
Yeah, the wide site GI was kind of focused more on the lower works and the upper works rather than in and around that sort of fault zone that we hit, really. So yeah, there was a tunnel that was identifying that.
I think, yeah, if we had the slide actually where you can see where we did the probing, if you extrapolate the angle up from that up to the hillside. It's basically on the side of a 45-degree slope, 600 meters above the lock. You know, you wouldn't be finding many people that want to mobilize a drill rig onto that location. So it would have been really difficult to get that from that area.
Or surface map it either.
Oh yeah. Aye.
Yeah,
Okay.
certainly the underground drilling was actually based on what we found both from the tunneling through the fault zone and the horizontal borehole through the fault zone. A lot of the subsequent underground drilling was targeted to try and intersect that fault with some success.
Max Caudle-Hazelwood from OTB. Question about the spoil. So you changed the scheme to include more tunnel and more galleries. Did you need to add extra area for the spoil on site because you're reprofiling the bank?
So rather than add extra area, we increased the height of the spoil storage area. And we obviously had to do that. Had to do quite a rigorous design check to make sure that slope at that height was still a sensible thing to do. And
we also had a much better idea at that point of what sort of bulking factor we were dealing with. So we could look at how much we'd actually use compared to what the design was and look at a sensible bulking factor and basically realize that, you know, we had been quite conservative early on. So we probably had more space to deal with than we would have had we not had that information.
Thanks.
All right. Any more questions out there? Yeah, couple here.
Shani Wallace from Tunnel Talk. Thanks very much for the presentation. Very good. Two questions. What type of rock bolts have you installed in the rock? And for this adit, if it becomes a permanent adit, will you have to line it?
I can go through the rock bolts. So yeah, generally, I think we use 6 different types along the whole length of the project. The most common was a 3 meter, 25 mil solid dowel. That was extended for the 3.6 meters for any of the wider excavations. When we got into the fault zone, we got a lot more sort of hollow dowels, so we were able to inject grout through those as we were drilling as required, and they could be basically self drilled anchors. Again, as the depth increased for the extension, we ended up getting in quite a stock of 32 mil steel dowels. Again, 3.6 meters long, so they were pretty serious, quite hefty ones. I think the only other thing we used was some of the fiberglass dowels. They were mentioned earlier. Actually, some of the longer ones we had to install through some of the wedge. I don't know if anyone's ever tried to install a rock bolt that's 32 mil thick, 9 meters long, but the self weight of that in itself, especially if you're putting that into grout, was near impossible to, except probably Charlie on site. He could probably have managed it. But anyway, fiberglass, much lighter, much easier. So yeah, that was picked for those locations. So yeah, basically a combination of solid, hollow, and then hollow fiberglass.
In terms of the adit, there's no intention of using it as a permanent tunnel. It was decoupled from the main works as purely an exploratory tunnel to acquire ground investigation data. So there's no intention for it to be used as a permanent hydraulic tunnel at all. As I said, if it's used as part of an access route into the, deeper into the mountain, there might need to be some design reviews carried out on it at the time, but yeah, no intention of as a permanent tunnel.
It's all galvanized, so should last a while.
Okay, was there one in front? No? Yeah, just there.
Hi, Sebastian Kumpfmüller from Dr. Partners. I'm wondering if the information that you gained from the excavation material, is that also investigated and looked into in terms of if it can be reused in the main works? Is that something SSE looks into and has gained valuable information now through the exploratory works?
Yeah, so we've got a lot of material now currently on site with hopefully the potential to reuse that some capacity for the main works. I'd say for this phase of GI, there's been lots of testing and investigation to kind of understand its properties and material makeup to make sure it's suitable. So there has been, you know, key kind of suitability assessments carried out on that.
Any more online?
We have like 15 at the moment. So, there is one about the water inflow. So they are asking, why do you think there was so little groundwater inflow from probing? And again, during the excavation, they are asking if is the lake water then mostly from surface streams?
No, I think that persistent water was possibly from streams above, but most of it would have just been pockets of groundwater. We had no real consistent flow like we saw in the probe hole. The only consistent flow was that rain shower. So yeah, just think it was pockets of groundwater.
That's one thing we haven't mentioned as well for the GI. There was also water strikes through the boreholes, and 2 of the boreholes are still open to this day, and we have flow meters on those, so we're able to leave them open for, you know, more than 200 meters of borehole each, almost 200 meters of borehole each, and we've got piezometers in them, so we can see how that fluctuates over basically a long period of time. And how that responds compared to, say, hydrostatic pressure, how that responds to the weather and everything. So that data is actually still coming in, as well as some extensometer data that's still being collected and reviewed on a regular basis.
Yeah, that wider groundwater and long-term ground monitoring piece isn't really something we've covered in the talk, but there was a lot of equipment, in situ equipment, which went into each of the boreholes, and which is continuously monitored now. It was all set up to be able to monitor remotely.
Thanks to geodata for that one. Actually, they should get a mention.
Okay. Yep.
Just one question from me. What is the expected design life of the tunnel? Like such a tunnel was like combined, construction methodology, I would say.
For the exploratory adit?
No, just for the tunnel. What is the design life expected for the tunnel?
For the exploratory adit, it was short term to allow us to conduct these works, but the permanent works will have a much longer design life for the whole scheme. Yep.
Thank you.
All right, one more online, and then one more if anyone's got one out there.
So they're asking how deep into the sidewall from the tunnel did you do your overcoring, and did you find the in situ stress that you predicted, and what was the sigma H, sigma V ratio?
Right, okay, I'll
That's a big question.
So, overcoring too close to the excavation is likely to give you quite misleading results. As a general rule, going 1 diameter or 1.5 diameters times so 1.5, so either the excavation span, length of the excavation span, or 1.5 times the excavation span is generally a good rule of thumb. Obviously, from a program and production point of view, we don't necessarily we want to start the overcoring as soon as we can. That was often done as a judgment call on site. Ultimately, we need to be overcoring in suitable rock. We may be in a situation where we've got suitable rock for overcoring without local fractures, which will give misleading results. So we might be in a position where we can do that within just over one excavation span away, or it might even be closer than that. We have to be a bit careful also about the blasting, the impact of a fractured radius around the excavation from blasting. But in general, we were never in a position where we would contemplate doing overcoring within that zone. In terms of the question about sigma, the overall K ratio, that was quite difficult to determine, as was the overall stress orientation as well. There's overcoring jobs which are quite straightforward, which give you which provide a good degree of certainty as to what that stress orientation and magnitude is. Coire Glas was not one of them. It was quite highly variable. I must admit, I've been proved wrong by the designers on this. I thought the number of overcoring tests we were doing overall, close to 20, was a wild number to do in such a small area. And the overall variability of the overcoring results we got were eye-opening, certainly. Are we in a situation, Norwegian type situation, where we've got a stress ratio of 3? Probably not. Have we got a stress ratio, potentially a locally high stress ratio? Maybe. But it's quite difficult to determine from the overcoring alone. What I would say is look at that in conjunction with the overall hydrofracture data too. And that analysis, that interpretation of it, isn't something I've done. So maybe Tom could answer that.
To put some numbers on it as well, we were normally doing the first cell after what, 8 meters or something, wasn't it? So, you know, and the diameter of the hole, 150 mil or something. So, you know, 8 meters of 150 mil core before you install the first stress cell, and then as many after that. The further you went in, the more and more difficult, or the more likely it was that you were going to have some sort of technical issue. Yeah, very difficult.
I mean, what you're really trying to do there is make sure the rock is good enough to do the overcoring test. There's no point doing an overcoring test in fractured ground, because you'll get an entirely misleading result.
Okay, one more question then. Yeah, down the front. Do you want to do it on the mic?
We
again,
didn't,
Lisa?
overall.
You can do it on the mic,
Yeah.
so everyone can. Yeah.
Did you do any, I might have missed this, any borehole logs vertically from the surface down to tunnel level?
Yes.
How many of them did you take?
Part of the wider site GI that Fugro carried out included a borehole that was 650 meters deep along, well, it was actually an inclined borehole in the vicinity of where the surge shaft is.
On the top of the mountain.
On the top of the mountain as well.
Rigs brought in by helicopter.
Yeah.
And
I was going to say, is the limitation on that just the cost and timing of how many you can do?
That was the only location that you've got flat ground in that entire area, basically.
Yeah, it was such a big operation getting in there to drill that single borehole. Yeah, and so there's only one borehole drilled from the top of the mountain, but obviously there's a spread of boreholes up in the upper works focused on the dam and reservoir location and the kind of upper control works as well. But yeah, that borehole that Fugro did to 650 meters was quite epic. It was pretty much a standalone operation up there with accommodation camps, 24-hour working, helicopter access in and out for people and equipment. So yeah, it was.
So basically, you're easier building a tunnel. I think should be the conclusion of the whole. Yeah.
Thank you.
Okay, if we can thank our speakers for a terrific talk. Finally, then, a couple of announcements. Yeah, drinks and food tonight, sponsored by STRABAG. Thank you very much. Just a bit of sad news. Anthony Umney passed away this week. Anthony was past chair of the BTS from 2002, 2004, and continued to stay involved as long as his health allowed him. And on that note as well, Terry MacDonald has also passed away in the last couple of weeks. So the family, there's not going to be a family funeral, but through Steve Parker, who's out there at the moment, and Tommy Gallagher, there's going to be a remembrance service in the ICE here on the 9th of October between 5 and 8 o'clock. The family fully in support of that. If you would like to attend, you've got the email there of Steve, or just get onto the BTS. So we know an idea on numbers as well. BTS fire safety and underground structures. So hopefully society members will have had an email now. They are seeking past events where there's been fire events in tunnels, so they can build up a bit of a picture on the causes and move best forward in how we're going to prevent. There's a QR code there if anyone's got any information on that, or if you would like to join the committee as well to get involved with that. So if you want to take, anyone who hasn't done the surveys interested in doing it, we do the scan now. Next meeting then is on Thursday, the 16th of October. And that's on HS2, a client's perspective. So that should be good. Speakers are Martin Nowak and Mark Lemon, sorry. Another very topical subject on Thursday, the 20th of November. It's a meeting on carbon management for metro projects, Copenhagen Metro. So the BTS are also, we've got our net zero group, which is building up quite a bit of momentum to try and provide guidance to the industry on getting down to net zero. And then the final one for this year, we've got on slip form tunneling. So not slip forms in shafts, but in tunnels, which is concept I'm told has been tried before, but never really took off. So it's where you build your tunnel lining without a precast lining. And we've got Professor Colin Eddy and Dr. Henry Paradou to talk on that. So Thursday, the 11th of November. All right. We'll be in a minute, I think.
Yeah.
Mike.
So for the BTSYM, we have the annual conference on the 24th of October at Arup office. So this is the last event of the term and the last event as me as a chair since last November. So we have the program quite on with a workshop at the beginning, 3 to 4 sessions, an open discussion at the end, followed by a social and networking at Arup office. The abstract application is open until the end of next week. And at the moment, we have some sponsors like Becker, Mott, Dr. Sauer, Tunneling Journal, Excalibur, and Ayesa. But the applications to be a sponsor of the conference are open. So please contact me or any of the committee who are around as well. So no paper is needed, only an abstract, and we will be shortlisting the abstracts by the end of the month, early October. And the next slide is just for you to know that the attendance is free for young members. So please get your ticket. And if you're not a young member, there are tickets available as well. So yeah, see you there. Thank you.
Okay, coming to the end. So the annual BTS Health and Safety course is now arranged on the 17th and 18th of November. So it's an excellent course, very good value, very good for, and STRABAG are a big supporter of this as well. The one thing to note is this year it won't be in the ICE building here, it's in Arab's office. So the website is open for booking now. So yeah. And one on the Harding Prize 2026. So the applications are now open to put in anyone who's interested in entering. Just a note on this, and last year we had several entries that never got past the client approval stage. So they were very good papers, but they weren't allowed to submit them. So if you're a client, we should be supporting this and really encouraging youth to come in. So if you're a client, if you can take a favourable view on that, and if you're a manager, encourage young members to submit papers. Okay, save the date. So the BTS annual or biannual conference is now set. It's in the Queen Elizabeth building just across the road there. and it's on the 6th and 7th of October 2026. The anniversary book is available. Hopefully a lot of you have got copies already. But yeah, they're still available via the website.